Okay, picking up where we left off at, we figured out that at x equals 2, since the second derivative of f of 0 is less than 0, this means that this is concave down. Since this is concave down at that point, right, concave down like this, then this point here, which is x equals 0, has to be a relative max. Also, since it's concave down, this part must be increase. So this part of the interval is increasing. This part must be decreasing. Hopefully that makes sense. Then I looked at this point at x equals 4. Notice that the second derivative of f of 4 was greater than 0. So this indicates concave up. If this is concave up, then at x equals 4, we must have a relative min, which means this part of the graph is decreasing, this part is increasing. So decreasing, increasing. Hopefully that makes sense. Alright, so let's look here. So we've figured out where the function is increasing, where it's decreasing, where it is concave up or down. We need relative min and max. We've got that. Any points of inflection. So we need, that's the only other thing we need is points of inflection. So, can't have a point of inflection here because the point doesn't exist, and that's where concavity changes, right? It's concave down, then it's concave up, so the only possible point of inflection would have been here, but since this point doesn't exist, you don't have concavity there. So we've done everything for, we've answered all of these. So, okay. We'll do example 3. So I guess I could start it here. Example 3, just like example 2, it's just a different function. We're going to go through this just like we did the last example. We're going to figure out where f increases, so a positive slope, where the slope is decreasing, where it's concave up or down, where there's relative mins or maximum values, and where there are points of inflection if there are any. Okay? So again, the first thing we have to do is analyze the domain. So let's look at this function. We could think of this as 1 over 1 plus e to the negative x, or 1 over 1 plus 1 over e to the x. Okay? And no matter what, the domain here is going to be all reals. So, first of all, we know the domain of this function is all reals. No matter what you plug in for x here, it's going to be a real number. Next, if we want to figure out where the function is increasing or decreasing, we are going to do the first derivative test, or you can use the second derivative test to figure that out. But we are going to have to take the first derivative. So let's do that. So if we take the derivative of this, let's do the Quotients Rule. It's going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the numerator squared. So now let's simplify this. Let's simplify the numerator. That's just going to become 0. This would become positive e to the negative x all over 1 plus e to the negative x squared. And then let's find critical numbers. So again, we could think of this as being 1 over e to the x all over 1 plus 1 over e to the x squared. Let's see if there's anything that I could plug in here that would make this equal to 0. Well, the only thing I can think of, because if you think of the function e to the x, it looks like this. Well, when x approaches positive infinity, e to the x approaches infinity. When this is infinity, that becomes 0. But that's not a real number, so that's not going to work. So there's nothing that's going to work there. Okay, so there's nothing that is going to make this true. Is there anything that will, is there an x value where the derivative does not exist? That's not the case either. So we have no critical numbers. If we don't have any critical numbers, we don't have any relative extremes. We don't have a relative minimum. We don't have a relative maximum. Let's move on to the second derivative. So let's take the derivative of the first derivative. Again, it's going to be the quotient rule. So it's going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So then we have to take the derivative of e to the negative x, which would be negative e to the negative x. All over 1 plus e to the negative x to the 4th power. Okay, so let's simplify this. Let's distribute here. So this would be negative e to the negative x. Ooh. Let's not do that. Let's look here. Let's look here. Let's look here. That reduces all the way through here, so this is going to be 1 plus e to the negative x to the first. This would cancel out. And then this would become 1 plus e to the negative x to the 3rd power. Now we can distribute here. This would become negative e to the negative x minus e to the negative 2x. Multiply these three together, it's going to be positive 2 e to the negative 2x all over 1 plus e to the negative x cubed. Then this would become negative e to the negative x plus e to the negative 2x all over 1 plus e to the negative x cubed. Okay, this can factor a little bit more. We can factor out e, or negative e to the negative x. That would just become 1. This would become negative e to the negative x all over 1 plus e to the negative x cubed. Now, define possible points of inflection. We need to figure out where the second derivative equals 0 and where the second derivative does not exist. For this one, we just figure out, is there an x value where the numerator would equal 0? This is the same as negative e to the negative x plus e to the negative 2x. Okay, and then what I could do, I could rewrite this, I could move this to the other side, so now we've got positive e to the negative x equals e to the negative 2x. Then I could divide both sides by e to the negative x power. So now I've got 1 equals e to the negative 3x power. Then the only way this would be true is when x is equal to 0. So we definitely have a possible point of inflection at x equals 0. Okay, for this one, we need to explore when the denominator, 1 plus e to the negative x cubed, equals 0. Is there a way to make that equal to 0? The answer is no. There's no way you can plug in an x value and make that equal to negative 1. So this is our only possible point of inflection. So what I'm going to do, we know our domain is all reals. We know our possible point of inflection is at 0. So we need to test this interval and this interval. See concavity, so I'm going to test the second derivative of negative 1. And over here I'm going to test the second derivative of 1. Here is our second derivative. So I think I'm going to need to finish this up on the next video.